Module 18, Lecture B, Meta Ensembles. By the end of this lecture, you will be able to apply AdaBoost and voting ensembles to combine base estimators, build stacked classifiers and regressors using cross-validated meta features, and prevent leakage when designing ensemble workflows. AdaBoost voting. AdaBoost basics. AdaBoost, or adaptive boosting, improves prediction by combining many weak learners, each performing slightly better than random guessing. Each new learner focuses more on the examples earlier learners misclassified, making small corrections over time. Together, these targeted improvements create a stronger overall model. AdaBoost is adaptive because each training round gives more weight to examples the previous learners got wrong and less weight to those they got right. This helps later learners focus on harder cases, such as subtle medical screening examples. Rather than memorizing mistakes, AdaBoost uses them to improve the combined model, often boosting performance even with simple learners. AdaBoost makes predictions by combining several learners, but it gives more influence to the ones that performed better during training. Unlike simple voting, where every model has an equal say, AdaBoost trains learners in sequence and adjusts their weight based on accuracy. This helps the final ensemble combine different decision rules into a stronger, more accurate prediction. Python code. AdaBoost basics. This example trains a small AdaBoost classifier, which improves performance by combining weak learners with adaptive weighting. It compares the result from a single decision tree with the result from boosted trees. We import key Scikit-Learn tools for building and evaluating an AdaBoost classification model. The breast cancer dataset provides the data. Train test split separates it into training and testing sets. And accuracy score measures how well predictions match the true labels. AdaBoost is used as the main ensemble method, with decision trees serving as the weak learners it combines to improve performance. We load Scikit-Learn's breast cancer dataset, a common example for classification tasks. The dataset is then split into input features and target labels, which represent each sample's class. This separation is essential for training and evaluating a machine learning model. Before training, confirm that the feature data and labels contain the same number of examples. If they do not match, raise an error because each data point must have one corresponding label for the model to train correctly. We split the dataset into training and testing sets to evaluate the model fairly and avoid test leakage. Using Scikit-Learn's train test split function, we reserve 25% of the data for testing. Stratifying by the labels keeps the class balance consistent in both sets, and setting a random state makes the split reproducible. We create a very shallow decision tree classifier with a maximum depth of 1, making it a weak learner. After setting a random state for reproducibility, we train it on the data so it can learn basic patterns. This simple model serves as a baseline for comparing more complex approaches later. This AdaBoost classifier uses 50 very shallow decision trees, each with a maximum depth of 1, as weak learners. A learning rate of 0.8 controls how much each tree contributes, while a fixed random state makes the results reproducible. AdaBoost improves performance by giving more attention to errors made by earlier trees as it builds the ensemble. AdaBoost is trained by combining weak learners and adjusting their weights to improve performance. A single weak decision tree is first tested to establish a baseline accuracy. Then, the AdaBoost model is tested on the same data. Comparing the two results shows how boosting can improve accuracy over one weak learner. The output reports the Scikit-Learn version for reproducibility, then compares test accuracy for a weak decision tree and an AdaBoost ensemble. The single tree provides a baseline, while AdaBoost shows the performance gain from combining weak learners. Its improvement comes from giving more weight to misclassified examples, so later learners focus on harder cases. This script shows how AdaBoost improves classification on a breast cancer dataset. It compares a single shallow decision tree, used as a weak learner, with an AdaBoost model built from 50 similar trees. After training and testing both models, the results usually show that AdaBoost achieves higher accuracy by giving more attention to earlier mistakes. The output reports the Scikit-Learn version and the test accuracy for each model. Hard voting. Hard voting combines several classifiers by having each model vote for a class label, then choosing the label with the most votes. It works best when the models make different kinds of errors, because the group decision can correct mistakes made by individual models. In this way, hard voting relies on model diversity and majority agreement, rather than a single model's judgment. Hard voting combines models by using each one's final prediction as a vote, so it does not require reliable probability estimates. This makes it useful for mixing different model types, such as decision trees and linear classifiers, into one decision. Its main limitation is that all votes count equally, so a weak preference can have the same influence as a highly confident prediction unless model weights are adjusted. Hard voting works best when the models are accurate but make different kinds of mistakes. Diversity can come from using different algorithms, features, or training data, so the ensemble can better handle disagreements. It should be tested on new data to check that it generalizes well and is not overfitting. Hard voting is valued because it is simple and easy to understand before moving to more complex ensemble methods. Python code, hard voting. Hard voting combines three simple classifiers by letting each model choose a class label. The class with the most votes becomes the ensemble's final prediction. We import key Scikit-Learn tools for building and evaluating classification models on the built-in breast cancer dataset. These include utilities to split the data into training and test sets, scale features, create pipelines, and measure accuracy. We also import several classifiers, including logistic regression, k-nearest neighbors, and decision trees, along with a voting classifier that combines multiple models into an ensemble. We load Scikit-Learn's breast cancer dataset, a common classification example, and separate it into inputs and labels. The feature data provides the variables used for prediction, while the target data contains the outcomes the model should learn to predict. Together, these give us what we need to train and evaluate a classification model. The code verifies that the feature data and target labels have the same number of entries, so each example has a matching label. If they do not match, it raises an error to stop the process. This check helps prevent misaligned data from causing unreliable training or evaluation results. The data set is split into training and testing sets using Scikit-Learn's train-test-split function, with 1/4 of the data held out for testing. The split is stratified, so the class balance stays the same as in the original dataset. A fixed random state is used to make the results reproducible. 3 classifiers are prepared for a majority voting ensemble: logistic regression, a decision tree, and k-nearest neighbors. The logistic regression and k-nearest neighbors models use feature scaling in a pipeline, while the decision tree is limited to a depth of 4. Fixed random states help make the results reproducible, and each model will vote on the final prediction. A voting classifier in Scikit-Learn combines several models to make one final prediction. In this case, logistic regression, a decision tree, and k-nearest neighbors are used together. With hard voting, the classifier chooses the class predicted by the majority of the models, helping improve accuracy by combining their strengths. First, the hard voting ensemble is trained on the training features and labels. Then, each individual model in the ensemble is evaluated on the test data by comparing its predictions with the true labels. The resulting accuracy scores are rounded for readability and recorded with each model's name, making it easy to compare the models with one another and with the ensemble overall. A single test sample is chosen to show how the hard voting ensemble makes its decision. Each model predicts a class for that sample, and the predicted label is converted into a readable class name. These individual votes are collected, so we can see how each model contributes to the ensemble's final prediction. The code uses a hard voting classifier to predict the class for one sample and converts that prediction into the corresponding class name. It then evaluates the ensemble on the test set by comparing its predictions with the true labels. This accuracy score shows how well the ensemble performs on unseen data. The code reports the Scikit-Learn version for reproducibility, then compares the accuracy of each model in the ensemble. It also shows how the models vote on one test case and gives the final hard voting prediction based on the majority choice. Finally, it prints the ensemble's overall test accuracy, so its performance can be compared with the individual models. This script shows hard voting with logistic regression, a decision tree, and k-nearest neighbors on the breast cancer dataset. After splitting the data and scaling features when needed, each model predicts a class, and the ensemble chooses the majority vote. The output compares individual model accuracy with the ensemble's accuracy and shows how the models voted on one test sample. Overall, it demonstrates how combining different classifiers can improve classification performance. Soft voting. Soft voting is an ensemble method that combines models by using their predicted class probabilities rather than only their final labels. Instead of simply counting votes, it averages or weights each model's confidence to choose the final prediction. This lets the ensemble make more nuanced decisions, especially when models agree on a class but differ in how certain they are. Soft voting works best when each model's predicted probabilities are reliable. Models should be more confident when they are more likely to be correct, but some algorithms may need calibration to achieve this. If one model is overconfident, it can unfairly dominate the ensemble's decision. For this reason, soft voting is most effective with accurate, well-calibrated models that make different kinds of errors. Soft voting combines the probability estimates from multiple models, helping preserve uncertainty while blending their different strengths. By averaging these probabilities, an ensemble can often make more reliable predictions than any single model. Models can also be weighted by validation performance, but those weights should be chosen carefully using validation data. Overall, soft voting is a simple, structured way to combine model confidence levels. Python code, soft voting. This example shows how soft voting combines the probability scores from 3 classifiers to make a final prediction. It then compares the accuracy of each individual classifier with the accuracy of the ensemble. This setup imports the main Scikit-Learn tools needed to build and evaluate classification models on the breast cancer dataset. It includes functions to load the data, split it into training and test sets, scale features, and measure accuracy. It also brings in several classifiers, including logistic regression, k-nearest neighbors, and decision trees, along with a voting classifier that combines multiple models into an ensemble. We load Scikit-Learn's breast cancer dataset, a built-in dataset for binary classification. The data is separated into input features, which contain the measurements for each sample, and target labels, which indicate each sample's class. This prepares the dataset for later processing and model training. The code verifies that the feature data and target labels contain the same number of entries, so every data point has a matching label. If they do not match, it raises an error to signal that the dataset is misaligned. This check helps protect data integrity before training or evaluating the model. Split the dataset into training and testing sets, so the model is evaluated on data it has not seen during training. Using Scikit-Learn's train-test split, reserve 25% of the data for testing, stratify by the target to keep class proportions consistent, and set a random state so the split can be reproduced. Three classification models are prepared for a later voting ensemble. Logistic regression and k-nearest neighbors are each built in a pipeline that first standardizes the features, with logistic regression using a fixed random state, and k-nearest neighbors using 7 neighbors. A decision tree is also defined with a maximum depth of 4 and a fixed random state, and all models are set up to provide probability estimates. A soft voting classifier in Scikit-Learn combines several models by averaging their predicted probabilities. In this case, it uses logistic regression, k-nearest neighbors, and a decision tree as the base classifiers. The final prediction is based on the combined probability estimates, which can help improve accuracy by drawing on the strengths of each model. We create a named collection of models to make training and evaluation easier. It includes logistic regression and k-nearest neighbors with feature standardization, a decision tree limited in depth to reduce overfitting, and a soft voting ensemble that averages the predicted probabilities from the 3 base models. This structure lets us loop through each model, fit it on the training data, and compare performance on the test set. This line displays the Scikit-Learn version used by the script. It helps confirm compatibility and supports reproducibility by showing that the code is running with the expected library setup. Each model is trained on the training data, then used to predict labels for the test data. Its predictions are compared with the true test labels to calculate accuracy. The model name and its accuracy, rounded to 3 decimal places, are then printed so the models can be compared easily. The first test sample is used to show how a soft voting ensemble makes a prediction. The classifier combines the class probabilities from its base models by averaging them, then reports the rounded probabilities for each class. The final predicted class is the one with the highest combined probability. This script shows how soft voting combines logistic regression, k-nearest neighbors, and a decision tree to classify breast cancer data. After training and testing each model, it compares their individual accuracies with the ensemble's accuracy. The soft voting classifier makes its final prediction by averaging the model's predicted probabilities, often improving performance by using the strengths of multiple classifiers. It also displays the combined probabilities for one test case to show how the ensemble reaches its decision. Stacking models. Voting regression. Voting regression combines several regression models by averaging their predictions into one final output. Because different models make different kinds of errors, this averaging can reduce the influence of any single weak prediction and produce more stable results. It is a simple ensemble method that improves reliability through model diversity without using a separate metamodel. Voting regression combines predictions from several models, much like averaging opinions from different experts. Because models such as random forests and gradient boosting may interpret the same data in different ways, averaging their outputs can reduce extreme predictions and lower variance. This makes the approach useful for noisy data or complex relationships, such as forecasting retail demand or travel times. Voting regression combines predictions from several base models using a fixed rule, such as averaging, while stacking learns how to combine them with another model. In voting regression, you choose the models and their weights, often starting with equal influence. It works best when the models are both accurate and diverse, because similar models may repeat the same mistakes, and weak models can hurt performance. This makes voting regression a useful final approach and a simple foundation for understanding stacking. Python code, voting regression. Voting regression combines predictions from several simple, diverse models by averaging them. This can make regression estimates more stable than relying on any single model. Comparing each model's error with the ensemble's error shows whether the combined prediction improves performance. These imports prepare a regression workflow using NumPy and Scikit-Learn. They include tools to create synthetic regression data, split it into training and testing sets, build several models such as linear regression, nearest neighbors, and decision trees, and combine them with a voting regressor. Model performance is then evaluated using mean absolute error, giving a simple way to test a diverse ensemble on unseen data. We create a synthetic regression dataset using Scikit-Learn's make regression function. It includes 300 samples and 6 features, with added noise to mimic real-world variability. A fixed random state ensures the same dataset is generated each time for reproducible results. To add nonlinearity and make the models more diverse, the target values are adjusted with a sinusoidal pattern based on the first feature. This creates more varied model responses and helps the ensemble capture more complex patterns in the data. Before training a model, confirm that the feature data and target data have the same number of rows. A mismatch means the data is not properly aligned and could cause training errors. If the row counts differ, raise an error so the issue can be fixed before modeling continues. We split the dataset into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is reserved for testing, and the remaining 75% is used for training. Setting the random state to 42 makes the split reproducible, which helps us evaluate model performance consistently. We define 3 regression models to add diversity to the ensemble: a linear regression model for simple linear relationships, a decision tree regressor with limited depth to capture nonlinear patterns while reducing overfitting, and a k-nearest neighbors regressor using 7 neighbors to predict from nearby data points. A voting regressor combines several regression models and averages their predictions to make one final prediction. In this case, it uses a linear model, a decision tree, and a k-nearest neighbors model. By blending these different approaches, the ensemble can produce more stable predictions than relying on a single model. The code trains a voting ensemble model on the training data. Each base model learns patterns from the input features and target values, and the ensemble later combines their predictions to improve accuracy on new data. To compare model performance, we set up clear labels for the linear model, tree model, neighbors model, and voting average ensemble. We then collect the fitted individual models and the ensemble into one group, so they can be evaluated in the same loop. An empty results list is prepared to store each model's mean absolute error for later comparison. Each fitted model is evaluated on the test data by generating predictions and measuring the mean absolute error against the true targets. These error scores are stored so the prediction accuracy of all models, including the ensemble, can be compared. The code first prints the Scikit-Learn version to support reproducibility and compatibility checks. It then reports each model's mean absolute error, rounded to 2 decimal places, so the individual models and the voting regressor can be compared clearly. To show how a voting ensemble averages predictions, we collect the prediction from each base model for the first test sample. Each model makes its own prediction, and these individual results are stored together. The ensemble then uses those predictions to compute the final averaged output. First, we show the actual target value for one test example, rounded for easy comparison. Then, we compare the rounded predictions from each base model with the voting ensemble's prediction. The ensemble prediction averages the base models, showing how their combined output can support more accurate results. This script shows how a voting regressor combines linear regression, a decision tree, and k-nearest neighbors on a synthetic regression dataset with slight nonlinearity. After training and testing each model, it averages their predictions in an ensemble and compares mean absolute error. The ensemble often performs better because averaging helps reduce the effect of individual model variation. A sample prediction also shows that the final ensemble output is simply the average of the base model's predictions. Stacked classification. Stacked classification combines several different base models, such as logistic regression, decision trees, or support vector machines, and feeds their predictions into a meta-classifier. The meta-classifier learns how to use each model's strengths rather than choosing just one model. Often, it uses predicted class probabilities, so the final decision can reflect each model's confidence. In stacked classification, the meta-classifier should learn from predictions that resemble real test-time behavior. Cross-validation creates these out-of-fold predictions by training base models on part of the data and having them predict the held-out folds. This lets the meta-classifier learn when to trust each base model, such as random forests or logistic regression, in churn prediction, without being misled by overly optimistic training predictions. For a stacked classifier, use diverse base models that make different kinds of errors, and combine them with a simple meta-classifier to reduce overfitting. If the base models are too similar, stacking may add complexity without improving performance. The meta-classifier should mainly blend the base model predictions, often with a regularized linear approach, while all preprocessing must stay inside the training folds to ensure reliable results on new data. Python code stacked classification. This script shows how stacked classification works. Cross-validation is used to create reliable meta-features, and accuracy is then used to compare the base models with the stacked model. This setup imports the main Scikit-Learn tools needed to build and evaluate a stacking classifier on the breast cancer dataset. It includes functions for loading the data, splitting it into training and testing sets, scaling features, and measuring accuracy. The ensemble combines models such as logistic regression, k-nearest neighbors, and a decision tree, with logistic regression also used as the final estimator. We load Scikit-Learn's breast cancer dataset, a common example for classification tasks. The dataset is separated into input features and target labels, which prepares it for training and evaluating machine learning models. The code verifies that the feature data and target labels have the same number of entries, so every data point has a matching label. If they do not match, it raises an error to signal misaligned data. This check helps protect data integrity before model training begins. The dataset is split into training and testing sets using Scikit-Learn's train-test split function, with 25% reserved for testing. Stratified splitting keeps the class proportions the same as in the original data, supporting a fair evaluation. A fixed random state makes the split reproducible across runs. We build a logistic regression pipeline that first standardizes the features so they have a mean of 0 and a standard deviation of 1. This scaling helps logistic regression work reliably with features on different scales. The model is then configured with enough iterations to converge and a fixed random state for reproducible results, combining preprocessing and training in one streamlined process. We use two base models in the stacking ensemble, a decision tree and a k-nearest neighbors classifier. The decision tree is limited to a depth of 4 and uses a fixed random state for reproducible results, helping it capture nonlinear patterns. The k-nearest neighbors model is placed in a pipeline with feature scaling, so distance calculations are fair across features, and it classifies using 7 nearby points. A stacked classification model combines several base classifiers so their predictions can improve overall performance. Here, logistic regression, a decision tree, and k-nearest neighbors serve as the base models, while another logistic regression model makes the final prediction. 5-fold cross-validation trains the meta-classifier more robustly, and the stack uses predicted probabilities so the final model can consider each base model's confidence. The training data is used to fit 3 base models: logistic regression, a decision tree, and k-nearest neighbors. Each model learns patterns in a different way. A stacked model is then trained to combine their predictions, learning how to use their outputs together to improve overall accuracy. We evaluate each model on unseen test data by comparing its predictions with the true labels. This includes the logistic regression, decision tree, and k-nearest neighbors base models, followed by the stacked model that combines their predictions. Comparing these accuracies shows whether stacking improves classification performance over the individual models. The script reports the Scikit-Learn version to support reproducibility, then shows the accuracy of the base models: logistic regression, decision tree, and k-nearest neighbors. It also prints the stacked classifier's accuracy using the same 3-decimal format, so the individual models and the stacked approach can be compared directly. This script shows how stacked classification works on a breast cancer dataset. It trains 3 base models: logistic regression, a decision tree, and k-nearest neighbors, then uses their out-of-fold predictions to train a logistic regression meta-classifier. After testing all models, it compares their accuracies. The stacked model is expected to match or improve on the best individual model by combining their predictions. Stacked regression. Stacked regression improves continuous predictions by combining several regression models through a second-level meta-model. The base models capture different patterns in the data, and the meta-model learns how to blend their predictions. This is useful when the target depends on varied structures, such as seasonal trends or regional effects, that a single model may not handle well. In stacked regression, the meta-model should be trained on cross-validated out-of-fold predictions, rather than predictions made on data the base models already saw. This avoids overly optimistic results, especially from flexible models such as decision trees or random forests. By using predictions from models that did not train on each specific example, the meta-model learns more reliable patterns and is more likely to perform well on new data. A good stacked regressor combines diverse base models that make different kinds of errors and capture different data patterns. Similar models usually add complexity without improving performance, so the goal is complementary strengths. The meta-model is often kept simple, such as a regularized linear model, and the whole workflow must prevent data leakage by doing pre-processing and tuning inside training folds. With cross-validated meta-features and testing on unseen data, stacking can turn several models into one more accurate and stable predictor. Python code, stacked regression. This example shows how to build a small stacked regressor. Cross-validation is used to create more reliable meta-features for stacking, and test scores are then used to compare the base models with the stacked model. We import NumPy for numerical work, especially arrays and mathematical computations. We also import Scikit-Learn for machine learning tools, including the make regression function, which creates synthetic regression data for testing and demonstrating models. We import the stacking regressor to combine multiple regression models and improve predictions. We also import linear regression as a simple baseline model, and ridge regression, which adds regularization to reduce overfitting. Together, these tools provide the main components for building a stacked regression model. We import 3 Scikit-Learn tools for building and evaluating a regression model. The mean absolute error metric measures the average size of prediction errors. The train-test-split function separates data into training and testing sets for fair evaluation. And a k-neighbors regressor predicts values by averaging nearby data points to capture local patterns. We import 3 Scikit-Learn tools for building a regression workflow: a pipeline creator to chain processing steps, a standard scaler to normalize feature values, and a decision tree regressor to make predictions from learned decision rules. A synthetic regression dataset is created with 600 samples and 8 features. Added noise makes the data more realistic, while a fixed random state ensures the same dataset is produced each time. This makes the setup useful for consistent model teaching and testing. To add non-linearity to the target values, a sinusoidal pattern is introduced by adding a scaled sign of the first feature. This makes the data more complex, allowing different models to capture both linear and nonlinear relationships and potentially improve prediction performance. Before training the model, the code verifies that the feature data and target values have the same number of rows. This confirms that each set of features has a matching target, which is necessary for reliable training. If the counts do not match, it raises an error to flag the data inconsistency. We split the dataset into training and testing sets so the model can be evaluated on data it has not seen before. 25% of the data is kept for testing, while the rest is used for training. Setting the random state to 42 makes the split reproducible, which helps compare results consistently across runs. The stacking setup uses 3 base regressors with different strengths. A scaled ridge regression handles linear patterns and multicollinearity. A shallow decision tree captures nonlinear splits. And a scaled k-nearest neighbors model uses nearby data points to learn local patterns. Together, these models provide diverse predictions for the overall ensemble. A stacked regression model combines several base models so their predictions can improve overall performance. Here, ridge regression, a decision tree, and k-nearest neighbors each learn different patterns in the data, while a linear regression model makes the final prediction from their outputs. 5-fold cross-validation helps make the base predictions more reliable and reduces overfitting. We train several models on the same training data: ridge regression, a decision tree, and k-nearest neighbors. We then train a stacked regression model, which uses the base model's predictions as inputs to improve overall performance. We evaluate each model on unseen test data using mean absolute error, which shows the average size of the prediction errors. This metric is calculated for the linear model, decision tree, k-nearest neighbors model, and the stacked model. Comparing these results helps identify which approach makes the most accurate predictions on new data. The output first shows the Scikit-Learn version to support reproducibility. It then reports the mean absolute error, rounded to 2 decimal places, for ridge regression, a decision tree, k-nearest neighbors, and a stacked regressor. Comparing these errors shows which model, or model combination, predicts the test data most accurately. with lower values indicating better performance. This script shows how stacked regression can combine several models to improve prediction. It creates a noisy, nonlinear regression dataset, splits it into training and test data, and trains ridge regression, a decision tree, and k-nearest neighbors as base models. A stacked regressor then uses their cross-validated predictions to train a final linear regression model. Each model is evaluated on the unseen test set using mean absolute error, so their accuracy can be compared, with the stacked model often performing best by combining the strengths of the others. Leakage-safe stacking. Cross-validated stacking. Cross-validated stacking trains a stacking ensemble while avoiding data leakage. Base models make out-of-fold predictions by training on part of the data and predicting the held-out fold. The meta model is then trained on these predictions, so it learns from outputs that resemble predictions on new, unseen data. In stacking, the meta model should learn from predictions that reflect real generalization, not from predictions a base model may have memorized from its training data. Cross-validated stacking does this by generating each training prediction from a model that was not trained on that same case. This gives the meta model a more realistic view of each base model's reliability and helps prevent overconfidence. The same separation between training and validation data is important in areas such as medical risk prediction, credit scoring, and fraud detection. In cross-validated stacking, the meta model is trained only on out-of-fold predictions, which helps prevent leakage and makes training resemble real-world prediction. After that, the base models are refit on the full training set, and their outputs for new cases are combined by the meta model. The fold design should fit the data, using random folds for independent records, chronological folds for time series, and grouped folds when related records must stay together. Python code. Cross-validated stacking. This example shows how to build stacking features without data leakage. It uses out-of-fold predictions, so the meta model is trained fairly, then compares test accuracy between leaky and leakage-safe stacking. This setup imports key Scikit-Learn tools for a classification workflow. It includes a function to create synthetic classification data, models such as random forest and logistic regression, and an accuracy measure for evaluation. It also brings in tools for splitting data, running stratified cross-validation, and cloning estimators so models can be reused consistently. We create a synthetic classification dataset with Scikit-Learn to demonstrate stacking in a controlled setting. It contains 900 samples with 12 features, 6 of which are informative for predicting the target. A fixed random state ensures the results can be reproduced. We use Scikit-Learn's train-test-split function to divide the features and target into training and test sets, with 30% reserved for testing. This gives the model unseen data for evaluation, while stratifying by the target keeps the class balance consistent in both sets. A fixed random state makes the split reproducible. Before training begins, the code verifies that the training data and labels have the same number of rows. This confirms that every feature set has a matching label. If they do not match, it stops with an error, so the data alignment can be fixed first. A base model is created using Scikit-Learn's random forest classifier with 60 decision trees. Each tree is limited to a depth of 4 to reduce overfitting, and a fixed random state makes the results reproducible. This model produces predictions that are passed to the meta model, supporting an efficient stacking process. The meta model is a logistic regression model trained on meta features created from the base model's predictions. Its solver is allowed up to 500 iterations to help it converge. and a fixed random state of 42 ensures reproducible results. A copy of the base model is made so the original stays unchanged. Then the copy is trained on the full training dataset. After training, it predicts class probabilities for that same data, and the positive class probabilities are reshaped into a column to serve as meta features for stacking. Because the model predicts on the data it was trained on, these meta features contain data leakage and are therefore called leaky meta features. A copy of the meta model is created so the original stays unchanged. The copied model is then trained on leaky training meta features and their labels, meaning it learns from predictions made using the same data involved in training. Finally, its training accuracy is measured on those same leaky features, showing performance on the training set while leakage is present. To generate meta features safely, use stratified 5-fold cross-validation with shuffling and a fixed random state. This keeps class proportions balanced across folds and makes the split reproducible. A copy of the training meta features is then filled with predictions from models that did not train on the corresponding data, helping prevent data leakage. Using stratified k-fold cross-validation, the training data is split into training and holdout parts for each fold. A fresh copy of the base model is trained on the fold's training subset, then used to predict positive class probabilities for the holdout subset. These holdout predictions are saved as training meta features, ensuring every stored prediction comes from a model that did not train on that data. We first make a fresh, untrained copy of the logistic regression metamodel using the clone function. Then we train it on the safe meta features and their labels, so it learns how the base model's predictions relate to the true targets. This lets the metamodel use those base predictions to improve its own predictions. A fresh copy of the base model is created, then trained on the full training dataset so it can learn from all available features and labels. The trained model then predicts class probabilities for the test data, and the positive class probabilities are kept. These values are reshaped into a single column so they can serve as meta features for evaluating the meta model. We compare the safe and leaky stacking models by measuring their accuracy on the same test data. Using Scikit-Learn's accuracy score, we check how each meta model's predictions match the true labels. This shows how the cross-validated safe approach performs on unseen data, and how the leaky approach performs despite relying on potentially overfitted training predictions. The output reports the Scikit-Learn version for reproducibility, then compares model accuracy results rounded to 3 decimal places. It shows the leaky stacking model's training and test accuracy, followed by the test accuracy of the cross-validated stacking model. This comparison highlights how the leakage-safe approach performs against the potentially leaky model on unseen data. This script shows how to build a stacking model without data leakage. It compares a leaky approach, where a random forest is trained on the full training set before creating meta features, with a safer approach that uses stratified cross-validation to generate out-of-fold predictions for a logistic regression metamodel. The leaky method can give overly high training accuracy because it overfits, while the cross-validated method gives a more honest estimate of performance. After testing both versions, the safe stacking accuracy is expected to be more reliable and often lower than the leaky result. Pass-through features. In stacking, pass-through features let the final metamodel use both base model predictions and the original input variables. This can improve flexibility because the metamodel can combine raw information with the base model's outputs, especially when those outputs leave out useful detail. For example, original medical variables such as age or lab values may help it judge which base model to trust. The key caution is to manage the workflow carefully so validation or test information does not leak into training. When using pass-through features in stacking, Avoid data leakage by ensuring every step is learned only from the proper training data. Out-of-fold predictions must come from models that did not train on the examples they predict. And pre-processing, such as scaling or imputation, must not use the full dataset. If validation data influences these pass-through features, evaluation results can look better than they really are, because future data would not be available during real use. To avoid leakage, pass-through features must be handled inside the same training pipeline as the base models and meta-model. Any transformation or feature engineering should be learned only from training folds and then applied to held-out folds, so the meta-model sees data that resembles truly new cases. For example, churn features may use past customer behavior, but not future spending. This lets pass-through features improve stacked ensembles while keeping performance estimates trustworthy. Python code. Pass-through features. This example shows leakage-safe stacking with pass-through, where the meta-model can use the original features along with base model outputs. It also compares results from safe preprocessing against leaky preprocessing to highlight the impact of data leakage. This setup imports the main Scikit-Learn tools needed to build and evaluate a classification workflow. It includes utilities to create a synthetic dataset, split it into training and testing data, handle missing values, scale features, and build processing pipelines. It also brings in several classifiers, including logistic regression, k-nearest neighbors, decision trees, and a stacking classifier that combines multiple models, along with accuracy scoring to measure performance. We create a synthetic classification dataset using Scikit-Learn's make classification function. It includes 800 samples and 8 features, 5 of which are informative for predicting the target. A fixed random state ensures the same data is generated each time, making the setup reproducible and useful for testing models with both relevant and less relevant features. We create a Boolean mask to find rows where the first feature is greater than 0.8. For those rows, we replace the second feature with nan to represent missing data. This intentionally adds incomplete values, so pre-processing steps such as imputation can be tested and applied. The dataset is split into training and testing sets using Scikit-Learn's train test split function, with 30% reserved for testing. Stratification keeps the target distribution similar in both sets, and a fixed random state makes the split reproducible across runs. Before modeling begins, the code verifies that both the training and test datasets contain rows. If either dataset is empty, it raises an error to stop the process. This prevents training or evaluation from running without the required data. We define 2 base models for a stacking classifier. One is a decision tree with limited depth and a fixed random state for reproducibility. The other is a pipeline that imputes missing values, scales the features, and then applies a k-nearest neighbors classifier. Keeping pre-processing inside the pipeline ensures each model uses only its own training data during cross-validation. A stacking classifier combines several base models to improve prediction performance. Its final model uses pre-processing to fill missing values and scale features before applying logistic regression. Pass-through is enabled, so the final model can use both the base model predictions and the original features. 5-fold cross-validation is used, so pre-processing happens within each fold, helping prevent data leakage. Fit the safe stacking model using only the training data, so the test set cannot influence learning. Then evaluate it by predicting the test labels and comparing them with the true labels. This accuracy shows how well the model generalizes to unseen data and whether the leakage-safe pre-processing worked effectively. This code creates a pre-processing pipeline with imputation and scaling, but applies it before splitting the data. Because the pipeline is fitted on the full dataset, information from the test set can influence the training process. This causes data leakage, a common machine learning mistake that can make model performance look better than it really is. Here, the data is split into training and testing sets after pre-processing has already been applied to all features, which creates data leakage. The split uses 30% of the data for testing, keeps the target class balance the same in both sets, and uses a fixed random seed for reproducibility. Because the test data influenced pre-processing before the split, the model may overfit and give overly optimistic results. A stacking classifier combines several base models and uses a final logistic regression pipeline to make the final prediction. That pipeline handles missing values, scales the data, and uses a fixed random state for reproducibility. With passthrough enabled, the final model can use both the original features and the base model outputs. And five-fold cross-validation helps evaluate performance across different data splits. However, this setup is part of a leaky workflow because pre-processing happens before the train-test split, which can let test data influence training. A leaky stacking model is trained on data that was pre-processed before the train-test split, so information from the test set may have influenced training. Its accuracy is then measured by predicting the test labels and comparing them with the true labels, showing performance that may be inflated by data leakage. The output reports the Scikit-Learn version for reproducibility, then compares the rounded test accuracy of a safe pass-through model with a leaky pass-through model. The key lesson is that pre-processing must be fitted inside the stacking workflow to prevent data leakage and produce trustworthy results. This script shows why pre-processing must be handled safely in machine learning, especially with stacking classifiers. It compares a workflow that fits pre-processing only within cross-validation folds against one that pre-processes the full dataset before splitting, which lets test data influence training. The safe approach gives a more trustworthy accuracy score, while the leaky approach can make performance look misleading. The main lesson is to include pre-processing inside the modeling workflow to prevent data leakage and protect model integrity. Leakage prevention. In stacking, the meta model must be trained on predictions that mimic results for unseen data. If base models predict examples they were trained on, their outputs can be too accurate and cause leakage, leading the meta model to learn patterns that may not generalize. To avoid this, use out-of-fold predictions, where each example is predicted by models trained on other folds. The base models can later be retrained on the full dataset for deployment. Data leakage can occur when pre-processing, feature engineering, or model selection uses information from the full dataset instead of only the training fold. In cross-validation or stacking, steps like imputation, scaling, feature selection, and pass-through features must be fit in a way that keeps validation data independent. The meta model should only receive inputs that reflect real prediction conditions, without future information or validation labels. Design ensemble workflows around the real prediction setting. For time-based tasks, train on earlier data and validate on later data. For grouped data, keep related records together so testing reflects new cases. Most importantly, prevent leakage by ensuring every step uses only information available at prediction time, so validation performance reflects real generalization. Python code, leakage prevention. This example compares leaky stacking with safe stacking. Safe stacking uses out-of-fold predictions to protect the meta model from seeing information it should not have during training. The reported scores show how leakage can make performance look overly optimistic. This setup imports key Scikit-Learn tools for a classification workflow. It includes utilities to create a synthetic dataset, build random forest and logistic regression classifiers, split data into training and testing sets, and evaluate accuracy. It also adds stratified cross-validation and cross-validated predictions for reliable model assessment, along with a pipeline and standard scaling to organize pre-processing and model fitting. We create a synthetic classification dataset with Scikit-Learn's make classification function for use in stacking. It contains 900 samples and 12 features, with 6 informative features that help predict the target, and the rest acting as noise. A fixed random state of 42 makes the dataset reproducible. We split the dataset into training and testing parts using the train-test-split function. 30% of the data is kept for testing, while stratifying by the target preserves the same class balance in both sets. A fixed random state makes the split reproducible across runs. Before training, confirm that the number of training feature sets matches the number of training labels. This ensures every input has a corresponding target. If they do not match, raise an error so the data split issue is caught before model training begins. The base model uses a pre-processing pipeline that first standardizes the features so they are on a comparable scale. It then applies a random forest classifier with 60 trees and a fixed random state for reproducible results. Combining these steps creates a simple, consistent workflow for training the model. A pipeline is built with a standard scaler and a random forest classifier, then trained on the full training dataset. It then creates probability-based predictions on that same training data and reshapes them into meta features. This is called leaky because the model is generating features from data it has already learned from, which can make performance look better than it really is. To create safe meta features, use stratified 5-fold cross-validation, so each fold keeps the same class balance. The base model predicts probabilities only for held-out training data, producing out-of-fold predictions that mimic unseen examples. Taking the positive class probabilities as a single feature helps train the meta model while reducing the risk of data leakage. 2 logistic regression meta models are built to compare stacking designs, using the same iteration limit and random state for consistency. The leaky model is trained on predictions made from the training data itself, which can make performance look too good. The safe model uses out-of-fold predictions instead, reducing data leakage and giving a more realistic performance estimate. A base model pipeline is built with standard scaling and a random forest classifier, using a fixed random state for consistent results. The pipeline is trained on the training data, then used to predict probabilities for the test data. These probabilities are reshaped into a single column to serve as meta features, supporting an unbiased evaluation on unseen data. We compare stacking performance by measuring accuracy in 3 cases: the leaky model on its training meta features, the safe model on its safe training meta features, and the safe model on untouched test meta features. These results show how leakage can make training performance look overly strong, while the test evaluation gives a more reliable view of real model performance. The output first reports the Scikit-Learn version to support reproducibility, then compares training accuracy from a leaky stacking approach with a safer out-of-fold method. It also reports the safe stacking model's accuracy on an untouched test set for a more realistic performance estimate. The key lesson is that meta models should be trained with out-of-fold predictions to avoid data leakage and produce more reliable evaluations. This script shows why data leakage must be avoided when building stacked machine learning models. It compares a leaky approach, where meta features come from predictions on the same training data, with a safer approach that uses out-of-fold predictions so the meta model learns from data it has not already seen. The leaky method can produce unrealistically high training accuracy, while the safe method gives a more reliable estimate of performance on test data. The main lesson is to train stacking meta models with out-of-fold predictions to prevent leakage and support trustworthy evaluation. In this lecture, you learned to apply AdaBoost and voting ensembles to combine base estimators, build stacked classifiers and regressors using cross-validated meta features, and prevent leakage when designing ensemble workflows. In the next module, Module 19, we will go over complex outputs.
Thank you for your attention. See you all in the next lecture.